Welcome everyone to the lecture 16 of the course Diffusion in Solids. Last week we talked about, we started talking about the atomic viewpoint of the diffusion process. So we started looking at how the random walk model is used to understand the atomic movement because that happens in random directions, and we saw that how that can be mathematically expressed in terms of average mean square displacement rather than using just the average displacement. So today then we are going to talk about some of the mechanisms of diffusion that are frequently encountered. So today we will be talking more about these four mechanisms. There are some more mechanisms which are operative more in the semiconductors or in the intermetallics, which we will take up when we talk about those specific class of materials. And before we go to this mechanism, I would also like to introduce, although we talked about the point defects in our previous weeks of lecture, but I would still try to tell a little more about, so that we round up our discussion well. So to begin with, we already saw what is vacancy. We have also derived what is the equilibrium concentration of vacancy. Remember, vacancy is an equilibrium defect, which means that at any given temperature there will be a certain concentration of vacancies which is always present in the crystalline material. And we have derived this relation which is x v is equal to exponential minus delta g f by kt. The reason I put 1 v here is because right now we are talking about the mono vacancy, and this delta g is basically can be written as delta h minus t delta s, and therefore it becomes exponential delta s 1 v f, that means the entropy of the vacancy formation multiplied by exponential minus delta h 1 v f by kt. So where as I written free energy of the mono vacancy formation. And we also saw that we represented graphically something like this. So this is your delta h and this is minus t delta s. More details we have to refer back to the lecture in the previous week, where we talked about how to determine exactly this value, which is the xv equilibrium, which is the concentration of the equilibrium vacancy. So we are talking about the mono vacancies. Then we also know that the enthalpy of formation can also be expressed something like this, minus dou ln xv by dou 1 over t. So just 1 second, I will just remove this. This t should not be there, because you see that delta g is delta h minus t delta s. So the entropy term does not contain the temperature. So therefore when you take the derivative of this with respect to 1 over t, this is what you get as the delta hv. So moving ahead, there is also a possibility of divacancy formation. That means two vacancies come together. So two vacancies, if they join together to form 2V, that is a divacancy. The equilibrium concentration of divacancies can be expressed as Z by 2, where Z is the coordination number, into exponential delta G of 2V B by KT, and multiplied by x1V equilibrium whole square. So it should be intuitive that the equilibrium concentration of divacancy will depend upon the equilibrium concentration of mono vacancies also, because they come together to form a divacancy. You may be wondering why this delta G term is coming as a positive. This is because that this is the free energy which is actually favorable for a divacancy formation. So usually you have to supply an activation barrier in order for, let's say, if you want to form a mono vacancy. But in the case of divacancy, there is an additional term. So there is those barriers in divacancy formation also, but there is also a gain in the energy when a divacancy is formed. Simply because if you form two mono vacancies at the separate places, more number of bonds have to be broken. Whereas if the two vacancies bind together, then the lesser number of bonds have to be broken. So the total vacancy concentration is equal to xV equilibrium is equal to x1V equilibrium plus twice of x2V equilibrium. And typically the divacancy concentration is higher near the melting temperature. Otherwise, as you go lower temperatures, the mono vacancy concentration is more dominating. Quite a lot of diffusion mechanisms, or when we understand the problems, we predominantly talk about the mono vacancies. Divacancies are still lesser in number. Okay, you can imagine also that this mono vacancies are in the order of 10 power minus 4. Then the square of it, it's already a lesser number. Now, a few points about the vacancy in the dilute alloys, that means where the solute concentration is very less. So in a dilute alloy AB, where B is the solute, the vacancies can form at A as well as B sites. That means if a B atom is removed, then the vacancy is said to be on the B site, whereas if A atom is removed, it is the vacancy on the A site. Now, depending upon the relative free energy of formation, so if delta G of mono vacancy, let's say for A is higher than the delta G for mono vacancy of B, then the vacancy solute interaction is attractive. Okay, that means the vacancy tries to be together with the solute. Whereas if the vacancy formation energy, free energy for A is less than vacancy formation free energy for B, then the vacancy solute interaction is repulsive. And according to a model proposed by Lohmer, the total vacancy concentration in a dilute alloy is dependent on the concentration of B. That means xV equilibrium is a function of xB, and it can be reduced, or it can be expressed as 1 minus Z into xB, exponential of minus delta G mono vacancy formation for A divided by KT, plus ZXB into exponential of minus delta G mono vacancy formation for B by KT. Here Z is the coordination number, XB is the solute fraction. So you can see if it was pure A, that means if XB is 0 and XB is 0 here, so this term goes to 0, this term goes to 0, this entire expression goes to 0, and you have only minus delta G mono vacancy by of A by KT. So that means this factor is what is the reduction in the concentration due to the presence of XB. So as I said here, the first term is the concentration of unpaired vacancies, which is reduced by a factor of 1 minus ZXB relative to that of pure solvent. So by this factor is the vacancy concentration reduced when you have a B atom forming, a B atom as a solute. And second term is the fraction of the solute vacancy pairs. So how many vacancies of the solute are there? So if we write this delta GB is equal to delta G 1V of A minus delta G 1V of B, then where the delta GB is nothing but the Gibbs free energy of interaction between the solute and vacancy, then some mathematical rearrangement we can do, and we can write xV equilibrium as minus delta G 1V A divided by KT. In the bracket, then we have 1 minus ZXB plus ZXB into exponential of delta GB by KT. So you can understand here again, if the XB is 0, then this reduces to the free energy or the vacancy concentration in the solute. and if the delta GB is high, then it leads to the enhancement here. Now, one thing that we actually did not talk about earlier when we talked about the defects is how to determine the concentration of this defect, especially the vacancy. How do we determine this vacancy concentration? We derived expressions for the equilibrium vacancy concentration, but how do we actually derive the vacancy concentration? So, there are a couple of methods I will mention. The first method is what is known as differential dilatometry. So, here what is the underlying principle is that the expansion of volume of metal because of increasing temperature. So, we know that as we increase the temperature, the volume of the metal expands, so it increases, and it happens mainly because of the two reasons, that there is expansion in the lattice parameter, that means the lattice, the atomic bonds, these are stretching, and the creation of more vacancies. So, creation of more vacancies, empty spaces also leads to the increase in volume. So, volume expansion means the increase in the lattice sites basically. So, the fraction of volume change is actually equal to the fraction of change in lattice sites, that is delta n by n. Now, the fraction of change is in linear dimension is delta L by A, and fraction of change in the lattice parameter is delta A by A. Okay. So, there is a lattice parameter changing and there is overall delta A by L by L that is happening. So, the linear change because of the creation of the sites and the vacancies is the delta L by L minus delta A by A. That means you can imagine that you have let us say a piece of your metallic sample. Now, when you heat this piece, there is an increase in the dimensions of the sample, that is where the delta L by A comes into picture. So, any linear dimension. Now, that has two components. One is due to the change in the lattice parameter, which is delta A by A. So, the remaining change, if you make the difference of these two, will be what is attributed to the change in the vacancies. So, this here is what is in terms of the vacancy change. So, this is how you try to calculate. Now, moving ahead, what we see is that in an isotropic structure, the change in volume is 3 times that of the linear change. So, if the structure is isotropic, then you simply calculate the change in one dimension and multiply it by 3, and therefore, we can write that the delta n by n, that is the change in the lattice sites, is equal to 3 times delta L by L minus delta L A by A. So, there are certain difficulties with this method also. One difficulty being that the concentration of vacancies even near the melting point is of the order of 10 power minus 4. So, even if we show a higher tolerance and ready to accept 5%, we need to be able to measure the length of the material and lattice parameter change in the range of 5 into 10 power minus 6. And the change in length and lattice parameter should be simultaneously at a particular temperature. So, the relation that is described above, that is let me just go back there once again, delta n by n equal to 3 times delta L by L minus delta A by A. So, this relation can be used for polycrystalline material with random orientation of grains or single crystals with a cubic lattice. In a poly crystal, there is some possibility of error also, because we neglect the grain boundaries and the grain growth. So, when you are measuring this change in length as a function of temperature, there is a certain grain growth happening, which also can cause some deviations. And if you use non-cubic material, if you want to determine the vacancy concentration in non-cubic materials, then the relation also changes slightly. For example, tin has a tetragonal structure, and for tin the relation should be the delta n by n is equal to 2 times of delta L by L in the A direction minus the delta A by A plus delta L by L in C direction minus delta C by C. Here A and C are the lattice parameter. And this is how the delta L by L and delta A by A, so very close. If when you measure, then you can get the value of xv. Now, just before we go to the next experiment, one thing you may be wondering, so how do we measure this delta L by A and delta A by A? So this is where the delta L by L is measured using the dilatometry. So basically the change in length. So you heat the sample and there is an extensometer attached in the dilatometer which can measure the change in length, and simultaneously because you are heating also, so what you get is the change in length over length as a function of temperature. So this delta L by L is measured using the dilatometry setup, whereas the delta A by A is measured by the help of X-ray diffraction. So basically with the X-ray diffraction you measure the lattice parameter, and if this X-ray diffraction can be carried out at the elevated temperatures, there are certain equipment, special XRD equipment which have attachment of what is known as a heating stage. So basically you can heat your sample to a higher temperature, hold it for a certain time, take the XRD pattern, and based on that XRD pattern you can derive what is the change in lattice parameter. So like that basically you derive the lattice parameter, and then like that at each temperature you can calculate the lattice parameter, and it gives you what is delta A by A. Another method, very important method of determining the vacancy concentration is what is known as the positron annihilation experiment. Positron is nothing but the antiparticle of electron and is represented as E plus. And these positrons, they combine with electron to produce gamma rays with specific energies. And when these positrons are bombarded on a solid material, it may travel for some time in the range of picoseconds before it combines with electrons. Now, positrons, when they are traveling inside the material, they get trapped in a bound state in a vacancy. As vacancies do not have core electrons compared to other atoms, it takes longer time for annihilation. So that means this positron wants to get annihilated by interacting with electron, but in between, if the vacancy comes, it gets trapped, and then the time for annihilation becomes more. So that's what if the higher concentration of vacancies is present, higher the half-life time for the annihilation. So if at a particular temperature half-life does not increase beyond a certain point, it indicates the equilibrium concentration of the vacancies. And based on this half time, one can calculate what is the equilibrium concentration of vacancies present in the material. And as I said, it is found to be the most accurate techniques to measure the concentration of the vacancies. So now going to the mechanisms of diffusion. The first mechanism is what is known as the direct exchange and the ring mechanisms. See, here we have to also understand that the mechanism initially, when if you read the history of the diffusion, I think we talked about it, that after Kirkendall showed his experiment, based on his experiments, it was understood that the defects like vacancies play a role, an important role in the diffusional process. Before that, what people thought is that the defects play actually no roles in the atomic movement. So that is where these mechanisms were proposed. So the direct exchange means, suppose if you have a tracer atom in your matrix, then simply this movement of tracer atom will go ahead or will happen with the exchanging the position with the A atom. Or it can also happen that there is a ring type of movement happening. So this atom goes here, here, and here, like that, and that's how the ring mechanism is done. And in this case, what then people thought that if these mechanisms are valid, that means in a binary alloy you will always have dA is equal to dB, because the rate at which the atom is moving is depending on, it involves both the atoms. So therefore, this rate should be equal. However, Kirkendall with his experiment showed that these rates are not equal, and therefore the vacancy mechanism was put forward, which is now well accepted in the field of diffusion, and it happens to be one of the most dominant mechanisms that exist in the material and the alloys. So these mechanisms, as I said, it postulated the equal rates of constituents in a binary alloy, and it was disapproved when the Kirkendall effect was established. Then we come to the interstitial and the vacancy mechanism. So interstitial basically mechanism means this is the position of interstitial atom before diffusion, this is the after the diffusion, and similarly in the vacancy mechanism the atom exchanges its position with the vacancy. So this is very important for self diffusion and diffusion in alloys. Just a couple of quick take home questions for you, that think of examples of alloys with the interstitial solutes and alloys with substitutional solutes, and which mechanism do you expect to be faster. There is also what is known as collective mechanism, where there is a collective movement of atoms, and this is more common in the amorphous materials or the glasses, where the periodic structure is not present. This is a schematic shown for a zirconium nickel glass. So it is a chain-like motion, and as I said, operative in undercooled or amorphous alloys. Then the divacancy mechanism basically refers to the change or movement of atoms by exchanging position with a divacancy. Then interstitialcy mechanism, interstitially remember is the difference between the interstitial and a solute and the interstitial C, or sometimes called as self-interstitials, is here the moment a tracer atom occupies the metallic, the parent metal position itself, and the parent atom is displaced into its own interstitials. That's why it is called as interstitial C or self-interstitial mechanism. So the movement happens by exchanging the position with this atom, the parent atom, which is acting as a self-interstitial. So it involves actually simultaneous movement of 3 atoms. That way it's a collective process, and in metals, however, this mechanism is negligible for the thermal diffusion. This is because the self-interstitials have high formation enthalpies compared to the vacancies. So if you see interstitialcy mechanism, it is generally seen in silver sublattice of silver halides or solute atoms in silicon. And as I said, that formation enthalpy for self-interstitial, SI refers to self-interstitials. This is almost 2 to 3 times of the delta H of the mono-vacancy formation. So that's why the equilibrium concentration of vacancy is much higher than the equilibrium concentration of the self-interstitials. So this becomes more important in the cases of radiation-induced diffusion, where the radiations are bombarded on a crystalline sample, and the parent atoms are knocked out of their position and occupy the interstitials. So as I already told, that when a crystal is irradiated with energetic particles, the lattice atoms are knocked out, and this atom itself is self-deposited or deposited in the lattice as self-interstitial. And when these defects become mobile, they both mediate diffusion and give rise to radiation induced diffusion, which is also causes the radiation damage in the crystals. Now interstitial diffusion, let us now try to understand that how do we relate this diffusion to the jump characteristics of the interstitial atom. What I mean is that, for example, if you look at here, or let's go to the interstitial picture. So here, for example, this atom, interstitial atom, is jumping to the next interstitial site. This atomic jump is happening, we understand there is a certain barrier also for it. But now how do I relate this atomic jump to the diffusion coefficient that I have understood before? So that is what we are going to do now for the interstitial diffusion case. So let us assume a plane of, let us assume a two-dimensional array of parent lattice atoms which are light blue in color, and then there is a B atom which is marked in a dark blue color, which is the interstitial atom. Now let us consider these two planes. This is the plane 1 and this is the plane 2, such that the interplanar distance is alpha. Now if let us say that the concentration at the plane 1 is N1 and the concentration at the plane 2 is N2. In this derivation, currently we are assuming that the lattice is a simple cubic lattice, and it's a very dilute solution. That means each atom is surrounded by 6 interstitial sites. Here I have shown a little bit extra purposefully just to make the picture more clearer to you. But in reality, what we are assuming is a dilute solution. So let us call gamma B as the number of jumps per second in random direction. That means an interstitial atom can jump in any random direction. Simple cubic lattice, that means it can jump in any 6 directions. And N1 and N2 are the number of B atoms per meter square in plane 1 and plane 2. Now what will be the flux of atoms from plane 1 to plane 2? The flux will depend upon how many number of jumps per second that happen and how many number of atoms are actually present on N1. So that means it happens to be gamma B into N1. And why by 6? Because gamma B is the total number of jumps per second, all 6 directions combined. Let's say if we want to consider only the movement in this direction, in the x direction, then we have to divide gamma B by 6. And the flux from plane 2 to 1 similarly is 1 by 6 gamma B times N2. So the net flux is equal to JB is equal to JB forward minus the JB reverse, which will be equal to 1 by 6 gamma B times N1 minus N2. Now how do I express this N1 and N2 in terms of the concentration, which is the concentration of B per unit volume? So if you think of unit cross section, then CB1, that means the concentration at the plane 1 can be written as N1 by alpha, and the concentration at the plane 2 can be written as N2 by alpha, because concentration is atoms per meter cube. So that means we have to see how much is the number of atoms divided by this volume. So you can work out yourself, satisfy yourself also that this expression holds true. So now if we move ahead, then this net flux JB is nothing but 1 by 6 gamma B alpha times CB1 minus CB2. Now this CB1 minus CB2, remember that what we are talking about is a very short or very small interplanar distance alpha. So which means that I can write, if I want to write dou CB by dou x, that means the derivative of CB with respect to x, it would be nothing but CB2 minus CB1 by alpha. That means the concentration of B at the plane 2 minus the concentration of B at the plane 1 divided by alpha is what gives me the dou CB by dou x. So this is comes by the definition of the derivatives itself. And now if you put this value here, what you get is JB is equal to minus of 1 by 6 gamma B into alpha square into dou CB by dou x. And if we compare this this relation with the Fick's first law, which is JB is equal to minus dB times dou CB by dou x, then we can see that dB is equal to 1 by 6 gamma b alpha square. So this, remember this relation we also arrived in the random walk theory. Only thing is that there we used gamma for the distance, the vector, the jump factors. Here it is alpha, but essentially the relation is same. So that dB is equal to 1 by 6 gamma b into alpha square. And you see that here the dB is independent of concentration. And just again one more self-study exercise for you. What do you think will happen to this relation if it is a non-cubic lattice? A very simple numerical to estimate the jump frequency of the carbon atom in gamma iron at 1000 degrees centigrade. The lattice parameter is given as 0.37 nanometer, and the value of D is also indicated here. So basically you can estimate what is gamma, and that answer comes out to be 2 into 10 power 9 jumps per second. So then talking about the temperature effects a little bit. So when you see that an interstitial atom is going from the initial state to the transition state, there is an activation barrier involved. This we saw in the previous lecture in the atomic jump we were talking about. So this activation barrier has to be crossed. And if the mean frequency of vibration is, let's say, nu, and for a unidirectional jump in one direction, the fraction of successful jumps to the next site is equal to exponential minus delta gm by RT. Now for the number random jumps in the 3D space, if Z is the coordination number, any sites are available. If the interstitial solute concentration is not that high, then the jump frequency is basically given by Z into nu into exponential minus Zm delta Gm by RT. That means this is regarding the barrier for the jump. So lesser is the barrier, higher will be the gamma. Similarly, nu is the mean frequency of vibration. If the atoms are vibrating with more frequency, then your jump frequency also becomes very high, and Z is the coordination number, how many sites it can jump to. Now this delta Gm can be written as delta Hm minus T delta Sm. So if we separate this, then it becomes Z into nu into exponential delta Sm by R into exponential minus delta Hm by RT. And therefore the D, which is 1 by 6 gamma b into alpha square, we can write it as 1 by 6 L alpha square. Put this expression. So this particular bracket terms include all the terms which are independent of temperature multiplied by exponential minus delta Hm by RT. And now if you compare this with the relation of Arrhenius type of relation, which is dB is equal to dB naught exponential minus Qi by RT, here the I refers to the fact that it is interstitial diffusion we are talking about. So this Qi is basically equal to the delta Hm. So this is the enthalpy of migration that we are talking about. So basically in the case of interstitial diffusion, the Qi is equal to the enthalpy of migration. When you talk about the vacancy mechanism, see the major difference comes is when especially when the solute concentration is very less. Then when it is interstitial diffusion, because interstitials are everywhere, then any direction an interstitial atom wants to jump to, it can jump with the equal probability. The interstitial sites are always available. But for the vacancy, because the vacancy concentration itself is very small, there has to be first, there should be a probability of finding a vacant site near to the movement, near to the moving atom. So therefore, here the additional term that comes into picture is probability of successful jump to a vacant site not only depends on Z, not only depends on the migration barrier, but it also depends upon the XV, that whether there is a vacant site available or not. So that, therefore the probability has this terms XV also. and therefore, as we know that XV equilibrium is nothing but exponential minus delta GV by RT. So, the gamma is written as Z into nu into exponential minus delta GV by RT into exponential minus delta GM by RT. And therefore, this gamma now can be written as Z nu into exponential minus delta GV plus delta GM by RT. This R or K usage depends upon which units you are using. So, as long as we are consistent in the solving the numerical with 1 unit, it should be fine. And now, if we further separate each of these free energies into delta S and delta H, what we get is Z into nu into exponential delta SV plus delta Sm by R multiplied by exponential of minus delta HV plus delta Hm by RT. And now comparing this with the Arrhenius equation, D equal to D naught exponential Q by R minus Q by RT, you get Q of SD. SD refers to as solute diffusion, substitutional diffusion, which is delta HV plus delta HM. So, this basically happens by the vacancy mechanism, that for this subscript SD is used. So, this Q SD is equal to delta HV plus delta HM. So, this will also give you a hint to the previous question that I asked, which mechanism you expect to be slower. Remember, in the case of QI, it was only delta HM, but in the Q of vacancy mechanism, the delta HV terms also come into picture. Then there are also interstitial substitutional exchange mechanisms. That means there are hybrid solutes which can occupy both the interstitial sites as well as the substitutional site. So, usually what happens is there is a trade-off, because the diffusion coefficient for the interstitial solute is usually higher than the diffusion coefficient for the substitutional solutes. However, at the same time, the concentration of the substitutional solute is less than the concentration of the equilibrium concentration for the interstitial solute. So, there are two types of mechanism: the dissociative mechanism, which is Bi plus V gives Bs, for example, copper in germanium, which means that basically an interstitial occupies a position and exchanges a position with the vacancy. So, this is known as the dissociative mechanism. So, you see that interstitial solute is interacting with the vacancy here, and the kick out mechanism is where the Bi is equal to Bs plus Ai. That means here finally when there is an exchange happening between the interstitial, and it occupies a substitutional position now, and a self interstitial is created. So, this is known as a kick out mechanism. Okay. So, the self interstitial is created. It is found in gold, platinum, zinc solutes in silicon, and zinc in gallium arsenide is few examples. So, with this now we end today's lecture on the atomic mechanisms. We will continue with deeper understanding of the correlation factors in the upcoming lectures. Thank you.